So today I shall start discussing on reversibility in cellular automata. Okay. So what is the meaning of reversibility? Let us first discuss. So actually in physics, so reversibility means there is no loss of information during evolution, right? So as thermodynamics says, a process is reversible if it moves from one state to another and then another, but it is possible to come back to its initial state. In fact, this is the meaning of reversible. Reverse, is in English. The reverse means you can go in backward. You can reverse it. So, since we are saying about evolution, there is a sense of time, right? So, so what I get, if process runs in back in time, it will return to initial condition without losing any of its properties. Okay, so from one state, from one condition, I'm moving to another condition, then to another condition. If it is reversible, then okay, I can go back to the original, right? So there's a sense of time is there, right? So in some sense, that in a reversible system, for a reversible system, if a condition, if a state is given to you of that system, that state contains all of its past. In what sense it contains? Because if you want, you can go back to the time, to the past. You can get information, exact information about the past. So, so this is the meaning of reversibility. So the term reversibility, is actually the people of physics, the physicists use the term mainly. However, nowadays, physics, people of physics, mathematics, the term is widely used. Take an example. So you can consider this planetary motion in orbits. It's a reversible system. See any planet, say let us consider Earth. Say today, now it is the in the orbit, Earth has some position. So to yesterday, what was this position? You can correctly find out. You can correctly calculate. Similarly, if you consider pendulum, a frictionless pendulum, right? So pendulum is oscillating. So if you know at any time, state or position, say here is the position of the pendulum, then at time t, what was its previous positions, right? Say at time t minus 1, say t minus 2, etc. You can uniquely determine, right? So the property of pendulum. I'm saying frictionless pendulum. So this kind of thing you can find in nature, very natural phenomena. And in subatomic world, in microscopic world, is very common. Say for example, consider the movement of electron around nucleus. So there are several orbits. The position as well as momentum, etc., the state of an electron, if you know that one, you can uniquely determine what are the position in previous steps. So here there is no loss of information. Okay, If there is a loss of information, you cannot reconstruct its past. You can reconstruct the system's past. So it is reversible, right? Anyway, as I've said here, in case of reversibility, there is always a sense of time, so there's a sense of evolution, right? Okay. Now come to the cell automata. This picture you have we have seen when Professor Kari was taking class, and he proved this one. He concluded his class with this diagram, where it says that inject surjectivity is equal to prejectivity is equal to no orphan is equal to balance property, etc. And in the trademark, what I've written here also, I mean, from the Kari's work, Kari's class, you can get it. Is actually injectivity equal to bijectivity. So he has proved it in a cell automaton. Injectivity implies subjectivity, and what is the meaning of bijectivity? Bijectivity means injectivity and subjectivity. Since injectivity implies subjectivity, so injectivity implies bijectivity. In first class he proved this one, and here in last class also he mentioned injectivity equal to bijectivity equal to reversibility. Okay, so why it is so? Why bijectivity and reversibility in this case? They're similar, the same. So let's say G is bijective. If G is bijective, G means is a global transition function of the CA, that is the G. If G is bijective, then what I can get? I can get an inverse, G inverse. G inverse exists, and from Headland's theorem, we know that this inverse is also a cell automaton, right? That in the last class, Professor Kari proved G is, if G is bijective, then G inverse exists. So in fact, it is true. It is always true. If G is a bijective function, you always find G inverse. This is one issue, but not the only issue. The point is here, G inverse is also a cellular automaton. G inverse I have written 0 to the power minus 1. Right? It's important. See, in case of cell automaton, you move from one step to another step, means one configuration another configuration by means of local computing. Now, in this case, what is saying? What it is saying? It is saying that you can find another local rule, okay, by applying which you can move backward. Okay, this is the meaning of this statement. So G inverse is also a cell automaton, right? That we have got from Headland's theorem. Now say a configuration X and G is bijective. So we move from X to Gx, the new configuration, from Gx to G square X, another configuration. In this way, I can move. Say so since it is evolving. Say if you consider, say X is at say time 0, then Gx is at time 1. So our system is discrete, so I'm considering here always time is discrete, right? So X, so here you can say that X is at time 0, then Gx at time 1, G square X. So you get this configuration at time 2 in this way. So Gx, G square X, the new configurations. In this way, the system is moving. CA is moving from one configuration to another, and then you can find to the power kx in this way. Now what I get here, G is bijective and G inverse is also cellular. Now if I apply in this way G inverse, see if I apply, just consider the first one. If I apply G inverse, uh, 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 I mean, here the new configuration. So there is a small typing mistake. Actually, I wanted to mean here from G to GX, then GX to G square X. GX is a new configuration, right? Here, so this line is erroneous actually. What I wanted to mean here, say GX is my new configuration. On this GX, if I apply G inverse, then I can get back this G. Okay, G square X is another configuration. If I apply inverse twice, then I can get the previous one in this way. So please correct this figure. Here I want to mean that its evolution is forward direction from x to j and gx to j square x to the power kx. If I apply the backward one, say j to the power kx, say if my niece say x dash, if I consider in this way, and if I apply g inverse one by one, then I can move in the backward direction. Okay, right. Please correct this figure. Uh, if you have any query, then let me know, or I can write it later. So, what I get is CA is reversible if and only if it is bijective, right? That I get. Although I have written already that bijectivity implies reversibility. Actually, that we can, from this discussion, we also understand that a CA is reversible if and only if it is bijective. Now, come to the reversibility issue of one-dimensional CA. We shall see later that behavior of one-dimensional cellular automata greatly differs with the behavior of two or higher dimensional cellular automata, right? So that we'll see. So first we are examining here reversibility case. So here we'll give a special treatment to reversibility of one-dimensional CA. Reversibility of one-dimensional CA was first successfully addressed by Amoroso Patt. They developed an algorithm, the first algorithm, Amoroso Patt's algorithm, in 1972. The paper was published. So now we shall discuss about the algorithm. Okay. So now to decide reversibility of a cellular automaton, we need to test bijectivity. Bijectivity means injectivity and cyclicity, right? So we shall test. We have to test surjectivity, right, and injectivity. Okay, so Amoroso Patt algorithm is two-part: surjectivity test and then injectivity test. However, we have already proved that injectivity of a CA implies bijectivity. So if you can prove injectivity, then you need not to separately prove surjectivity. However, if you want to decide whether a CA is surjective or not, if you only want to decide that part, then you have to use this algorithm, Cytogetus algorithm, right? Amoroso Patt, they proposed uh, both the algorithms. Okay, although we are discussing reversibility, and to decide reversibility of one DCA, injective test is sufficient, but we shall start with surjectivity test. Okay, so how to test surjectivity test? So you have to test whether G is surjective or not. And surjective means, what is the meaning of surjective? You'll find a configuration which has no pre-image. So therefore, you have to search for a configuration without a pre-image. And if there exists one such configuration, then that automaton is not surjective, right? So the challenge is, see, your system is infinite system. There are infinitely many configurations, right? So you cannot do it. You cannot run and decide. You cannot run and decide. You cannot test all the configurations, right? If the system is finite, then it is at least theoretically possible. Well, you shall test all the, you shall consider all configurations. So then you'll decide. In this case, no matter how much time, how much space given to you, you cannot decide it. Okay, so you need some innovative idea, a new algorithm by which you can decide this one, right? So you can do a simple scan. Say, suppose a table is rule table is given, as rule is given. Okay, we are discussing. Recall that we are discussing sometime rule can be expressed, can be presented in tabular form. Hmm. So suppose in one-dimensional case it is very common and we can do it. So suppose a rule is given, rule table is given. Okay, and what you can do, you can simply do one thing. Suppose you have S, right? S is the symbol set, the state set, right? Now find if there exists a symbol which is not in your symbol table, okay, which is absent in your rule, actually it's in the symbol table, okay. And if it is so, then it cannot be surjective. Take an example and be clear. Consider this is your rule table, okay. The next day, the second column is actually the rule, and first column here I am showing the argument. I have considered three neighborhood CA. Three neighborhood means m equal to 3, right? So, and there are three states, 0, 1, 2. Okay. Suppose S is equal to 0, 1, 2, three states. So in the domain, how many values you can get from all 0, 0, 0, 0 to 2, 2, 2, that you can get. And function means, please recall that how we represent the next function or rule. For each value, each domain value, I can get a function value that that I have written here in the table. Okay, so next state means against that domain, what is the what is the function value, right? Now see, it is a three-state CA because S equal to 0, 1, 2, right? So now in the next value, you can see only 0 and 1 present. 0 and 1 are present. There is no 2, right? So that is here written. If there exists a symbol in S which does not exist in an image of any M tuple under local rule R, right? That symbol 2 is absent in rule table, means next state in the rule, next state is a next state, this values of next, the next state that constitutes, these values constitute the rule. In that rule, you cannot find 2. Now let us consider a configuration all 2. Is it possible? Can you get any pre-image of this configuration? You can never get, na. So if you consider 2, 2, 2, so from no configuration you cannot get 2, right? Because so if one configuration is given, how can I find out the next configuration? By using the rule table. But rule table is showing that in the next state there is no 2, right? So then how can you get this configuration 2, 2, 2, all 2? So it means it has no predecessor, right? It has no predecessor. Okay. You can you can test it, right? So therefore in this case, existence of such a tool tells us that the CA is not surjective, right? Is this point clear? Stop me if you have an issue. Oh. In fact, in the Kali's class also, Kali was finding the predecessor. So in this case, you cannot find any predecessor. There is, you cannot get any configuration from which you can get this all 2. So by the simple scan, you can decide if you find non-existence of a symbol in the nested values, right? There is another property called balance property. Okay, that is called balance property. That property also was discussed. See, all the symbols have equal share in the table, right? And if the CA is balanced, then it is not balanced, it is not surjective. That is also, this also proved by Curry in one of his lectures. So that is also proved, he developed some style, etc. So I'm not going to do that part. The rule given in right hand side, that is obviously not balanced, because here there is a 2. Okay, and here also you can find the number of ones and number of zeros. They're not same. Number of zeros is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And number 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 14 zeros, 13 ones, and 0 twos. So it's not balanced. Okay. So take this CA. Okay, this is another local rule. A CA is designed by this local rule. Okay, so now here you have 2 states, 0 and 1 only. Okay, only 0 and 1 you have, and 3 neighborhood. I mean, neighbors only. A cell, suppose a cell depends on self, left neighbor and right neighbor, right? And see that this rule is balanced. Why it is balanced? See, number of 0 is 4 here, 1, 2, 3, 4, and number of 1 is also 4. So it's balanced, right? So, therefore, from balancedness property, you cannot say it is not surjective. But can we say that it is surjective? No. Just looking at a local rule, it cannot decide whether it is surjective or not. So then what I have to do? I have to find the predecessor of configurations. So there are many configurations, say all 0, all 1, 0, 0, 0, 1, 0, 0, etc. Right? So let us find out. Let us take this one. I have to do. I'm trying to use the jam. Let me see whether I can use it or not. Just let me use this one. Can you see the board? Please accept that one. I have just opened that one. I've shared with you. Hmm?
You can see.
You can see?
Yeah.
You can see, no?
Yeah.
Okay. Say late, but consider say 0. Say 0, 0, 0, 0. Okay. Okay. These are the say some configurations were there. So if you recall, I have to go back that part again and again. So I have to just see if it is 0, 0, 0, it is 0. Okay. For 0, 0, 0, it is 0. So if I find oh, why it is gone? I'm not getting. Okay. So then, so from this 0, 0, 0, suppose I am having this 0, 0, 0, this configurations I am having, right? Now, from the 0, 0, 0, I have to find whether it is having any predecessor or not. I know from 0, 0, 0, I can get 0. So if I write here this 0, 0, 0, 0, 0, then I know from this configuration I can get the next configuration. From this one, I can get the next one. Right? So therefore, 0, 0, 0, 0, if I consider this configuration, it has a predecessor. Now, if I consider, say like all 1, say I'm taking another example, say all 1, say all 1. Of it is better to use the whiteboard. So all 1s are there. See, please see the that one. that rule table. What are the rule table? Just um, see, here is a 0 1 0. From 0 1 0 you can get 1, right? From 1 1 0 also you can get 1, 1 0 1 also you can get 1, and 1 0 0 also you can get 1. So these are 4 options from where you can get 1, right? I'm taking this 0 1 0. So if I consider 0 1 0, then it will be 1. So keep this in mind. Then what I'll get, okay, there's a problem. What I'll get, so I'll get like this. So it will be, if I write here 0 1 0, 0 1 0 is 1, and what is 1 0 1? Please see, it is 1 0 1 is again 1, no? 1 0 1 is again 1. So from this 0 1 0 I am getting this one. It's okay. From 1 0 1, from this 1 0 1 I am getting the next one. Now again I am putting here 0. Then what I'm getting, from 0 1 0 I am getting this one in this way. So if I write in this way 1 0 1 0 1 0 1 this way, then you'll see that it's possible to get this configuration. So therefore, if you consider all 1, it has a predecessor, right? 0 1 0 1 0 1 etc. You are you'll have this one, this configuration. From this configuration you can get, say, all 1. So I'm giving a sample example, how can I find the predecessor of a configuration. Now let us consider a configuration like all 0, then 1, say, then all 0. A single 1 is in another configuration. There are many configurations. This is another one configuration. Okay, say all 0, so middle only 1 is there. Say if you consider the rule table, then you'll find it is 0 0 0. See, there are all 0 are there. See, you have all 0. So I know in this example also, in this case also, I have seen that okay, if there are 0, then I can get 0 easily. But here it's thin about case. Here I have to get 0. In this cell, I have to get 0. So how can I get this one? See, if I put, please come, go back once again to the rule. Again, I know there will be problem, but still. See, when I get 0, if it is all 1, then it's 0. Right? 0 1 1, then it is 0. And 0 0 1, it is 0. If it is all 0, then also 0. Okay, so you can get all 0, all 1 case. So two cases are there. 0 0 1 is 0, and 0 1 1 is again 0. Right? Now in that cell, I want to get 0. In that cell, in this cell actually, I'm talking about this cell. I want to get 0. In this cell, I want to get 0. So what two options? Recall that if it is 0 0 1, then is 0, and 0 1 1. Right? So if I put here 0 0 1, says if I put here 0 0 1, then I can safely get here 0 0 1 is 0, 0 0 1 is 0. So then here next is I have to get 1. So this part is done. So 0, 0, 0, 0, 1, I have received this 0, no problem. But now I have to get this one. This 1 I have to get. Now I already have seen in this example, 0, 1, 0 is 1, right? So if I put here and see 0, 1, 1 is 0. So note that 0, 1, 1, this is 0. But 0, 1, 1, 0, 1, 0, sorry, 0, 1, 0, this is 1, right? So you have, if since you have put here 0 and 1, you have only option, you have to put here 0, because we are matching now. So I can get 0, 1, 0, 1, 0 is 1. Now next point is you have to get 0. So 1, 0 you have already put. But you'll see that 1, 0, 0 is 1, and 1, 0, 1 is also 1. So both are 1. So you cannot get this one. So you cannot get 0 here. Right? So if you follow this setting, up to 1, okay, you are able to construct this some part of predecessor, but finally you cannot get this 0 for any neighborhood configuration, for any kind of neighborhood. So this will not work. So therefore, at least in this way, you cannot get the predecessor, right? Right. There is another option you can think. See here, what I done here, what I done in this case, 0, 1, 1. I have put here. I have taken 0, 0, 0, 1. I have taken 0, but I also know 0, 1, 1 is also 0. So let us. So it will not work. So let us cross it out. So then I am constructing a new one. So here 0, 0, 0, okay, and 0, 1, 1. Now here 0, 1, 1, it's also 0. It's no problem. It's also 0. I can get it. Now I have to get this 1. This 1 I have to get. So where I can get this 1? 1, 1. Can I get this 1 here in this setting? 0, 1, 1 is 0. It's okay. But here 1, 1. I can get 0 or 1 here. I can put in this cell either 0 or 1. If I put 0, if I put 0, if I put 0, I'll get 1, 1, 0. Right. If I put 0 here, then I'll get 1, 1, 0. What is the value of 1, 1, 0? 1. Right? Can you recall what is the value of 1, 1, 0? 1, 1, 0 is 1. Right? Then, then the same problem here. Same problem here. So for this, so if you want to get the 0, then 1, 0, 0 or 1. But we have already seen that if you have 1, 0 here, for 1, you have already seen that for 1, 0, if you put 0, then it is 1. If you put 1, then it is also 1. So these 0 you cannot get. So therefore, this style also will not work. So what I get? I get that this configuration has no predecessor. So a configuration which is having a single one but all zero, it is having no predecessor. So this is a Garden of Eden configuration, right? This configuration we call Garden of Eden configuration. Now, since such a configuration exists, therefore that we can see it um, is not subjective, right? Now come back to my presentation. Okay, so here what we have seen that say we have tested with C configurations only. So all 0, 0, 0, 0 is having a predecessor, all 1 is having predecessor. But if I take all 0, then 1, then all 0, then it has no predecessor. Now, how can I find out this one? There are infinitely many configurations. There is a challenge now. You have infinitely many configurations. How can you search? For searching, for efficient searching, Amoroso Patt, they gave one algorithm. Okay, so they actually proposed a method by which you can efficiently find out such a you know Garden of Eden configuration. Okay, how it works? Amorph Pet works. It constructs a tree. So now I shall tell you the construction, but it constructs a tree. Very interesting, very simple and very interesting. Let me start the algorithm, then we'll come back to the example again. Okay. First step, uh, determine if a symbol S exists, which is not the image of any M tuple under R. Okay. So the first point that the simple scan I have discussed, that if such a symbol exists, which is not present in the rule table, right? I mean, in the next value, that value doesn't appear. If such a symbol exists, G is not surjective. Okay, and algorithm stops. Otherwise, it proceeds. Recall that just now I have said that if a rule is unbalanced, not balanced, then also it is not surjective. However, Amoroso Patt, their algorithm does not use that property exclusively. Okay, that property is not used. So in my discussion, this balanced I shall not use. Okay, so even if it is unbalanced, then also I'll run the algorithm. So second step, what is saying? As I've said, the algorithm constructs a tree, and the tree is a rooted tree. So level 0 is the root. What are the contents of the root? Contents is some domain value of the nested function, means some m tuple. So m is our neighborhood. In my whole discussion, I have said before that m is the neighborhood. So there are m tuples. So a1, a2, am. Okay. So so these tuples are the member of node. But it is a style how to select that node, how to select this m tuples. So it's saying that select an element, any element B. So any element B, and construct the root, node at level 0 means the root, such that A1, A2, AM, okay, some symbols, A1, A2, AM, the symbols of S, and G of A1, A2, AM is equal to B. Okay. If the next state, uh, sorry, it will be R. Huh? So there is again a mistake. It will not be G, it will be R. So in level 0, what I've written, please note that I've written here G, but it will be R. Okay. So let me correct it. Sorry. Let me correct it. Otherwise, it will be R. Right. Mm. So,
Sir, another point is there. Sorry.
oh,
Next,
sorry.
next step also probably the same mistake is there.
Okay. Okay. I'll check. Okay. So, so the R is my rule. R of A1 AM is equal to B. Okay. For any A1 to AM, if it is B, then A1 to AM, they are the members of the root. Right. In this way, I form my root. Okay. Then, so just first note the points, and if I give the example, it will be clear. It will be clear. Hmm. Now, from that root, I construct the nodes of next levels. So from first level 0, then level 1, it will be level 1. Hmm. So uh, so I am constructing here, NA, a new node from say root. If it is level 1, then I'm constructing NA from the root. What is the A? A is some state. For A is a state in S, a state actually. Now, I'm forming in this fashion. Suppose S is in S, small s, consider small s. Now then, here again I'm saying it will be R. R of A2 AMS is equal to A. Right. So A2 to AM. So actually I'm shifting one room. So it was A1 to AM. Okay. It was A1 to it was A1 to AM. So I'm shifting that neighborhood structure by one position right. So A2 to AM and S, such that R of A2 AM is equal to 1. So again, some typo are there. So it will be A2. It will be A2. Okay. Okay. Let me use this style. I mean, not that one. Let me use this style. Okay. No animation required. Well, so take an example. Suppose in next slide I have an example. Suppose it's equal to 0, 1. Okay. And so this is my example. The example I've given first. Okay, this is the example I have taken. This is a balanced rule. So this is my first node, root node. See, I have considered b equal to 0, means state is 0. See here, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. They are all 0. Okay, 0, 0, 0, 0, 0, 0, 1 is 0, 0, 1, 1 is 0, 1, 1 is 0. Okay, so these are forming my root node, right? Okay, you can start with 1. So don't ask me that why it was 0. I have taken 0. You can start it with 1 and you'll get the same result. Okay, so this is the beauty of the algorithm. Will get the same result. You can start with sorry. You can start with any state, right? Now from this I am getting the nodes of level 1. Next one. See how I'm getting. See from the 0, 0, 0, I'm getting 000 as well as 001. See, there are 4 entries. In level 0, there are 4 entries. Right? There are 4 entries. Right? Now, for each entry, I can get 2 entries. Two neighbor configuration. Why? Because I am shifting it one position left. Sorry, one position right. So from 000, I can get 000 and 001. Similarly, from 001, I can get 010 and 011. So let me use again a board that will be more clear. So let me first explain, then I shall use the board if you need. Then from 011, if I shift one room, if I want to shift one room right, then I can get 110 and 111. Right. Similarly, for 111, I can get 110 and 111. So I am getting new 6 entries. For 000, 2 entries. For 001, 2 entries. For 011, 2 entries, and 111 the same. So no entry for 011 because they're same. So I'm getting 6 entries. See, in right hand side, I've written 6 such entries. 010. You can see here. So here I'm saying 000, 000, and 001. 00 is here and 001 is there. From 001, I'm getting 010 and 011. So here 010, 010. Here you can find 010 and here 011. In this way, I am getting this M neighborhood structure of the next levels. Right? Is this clear? Or should I use the board? Now I am dividing them into sides. How I'm dividing? See, so that is saying my algorithm. See, in the step 3, here what is saying? For each A, construct node A. Okay, and here I am getting A2, AM, S. Here S can be 0 as well as 1. Okay, and how I'm clubbing? If G, A2, AM, S is 1, then they are clubbed in one group. Right. So here, what I've done? 010 and 110. 010 and 110, both are 1. Right? 110 is 1, 011 10 is 1. So they are clubbed in 1. And I have put a 1 here. You can see 1. I think you all can notice my mouse pointer. So here I have written 1. So and from this one, I'm getting this one, this node having 2 entries. Whereas see, in the lower node, this one 000, 001, 011 as and 111 all are 0. You can see 000, 001 and 011 as well as 111. They all are 0. So they put in another basket. So this is the root. L0 is the root node. From this node, I am getting 2. I am getting here two nodes. And if my state set contains say m number of say k number of state, then I may get k number of children from one node. Right? Here, see, S is equal to 0 and 1, so I can get this 2 node. And so I'm saying it is N0. So this one, I'm saying it's N0. I'm saying it's N1. So as the convention of the algorithm, it is saying you say it in A for A belongs to S. Okay, so here A is 0, so then 0. And if A equal to 1, then N1. So I get, two nodes. In this way, I have to proceed. In this way, I have to proceed. Now, see, interestingly, in the root, there are 4 nodes: 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1. And this one, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, they're same, exactly same. Right? It is exactly same. Now, so if I proceed further, then what will get? The behavior of the root node and behavior of this node will be same, because the these domain values or neighborhood configuration which are constituting the node, they are same. Since the construction of a net of a node is same with the other, so then the number of the further processing, if I process further, I'll get the same result, right? So it shows that I need not to proceed with this duplicate node. These type of nodes are named as frontier nodes. This name was given by Amoroso Patt, so we call it frontier node. So we mark it star. So in my algorithm, I need not to proceed with the frontier nodes. So then I have to proceed with only one node, only one node. Okay, so 2 nodes we have listed, but I have to proceed with only one node, right? So let us proceed. Let us proceed. So in next one, in a similar style, there are 2 1 0 1 0 and 1 1 0. If I shift one room right, then from 0 1 0 I'll get 1 0 0 and 1 0 1. I have 2 options. But for the both the cases, for the second one also 1 0 0 and 1 0 1, I'll have two options, right? So here I'm getting 1 0 0 and 1 0 1, and both of them 1 0 0 as 1 0 1, they are having next level as 1. See, 1 0 0 is 1 and 1 0 1 both are 1. But what algorithm is saying? Algorithm is saying, see, look this. For each A, I have to construct NA. So for if any A equal to 1, I have received N1 for this level. But if N equal to 0, if A equal to 0, I cannot get this A0 N0. This one I cannot get, this is the empty one. Right? This one is empty. This empty node I have received here. Right? What to do with this empty node? These empty nodes, they have the Amoroso Patt, they have given the name as terminal nodes. Okay. Now, algorithm terminates if it gets terminal node. Okay. And they are saying, if you get terminal node, then declare that CA is not surjective. Right? CA is not surjective. Okay, let me come back to the algorithm part again. Here, what I have written. So this part is clear, I think. So step 3 is clear. So for each A1 AM in N, if no such S is there, then it's not included. NA is not included. So I have said that if N is called terminal node in the graph, that NA, if so, you can find any S. So it's called terminal node. I have said what is the meaning of terminal node. And existence of a terminal node means the path starting with root to that terminal node indicates a sub-configuration with no preimage. That is, we have received an orphan. Okay, what is orphan? In a configuration is a finite length pattern which has no pre-image. So in any configuration, if you find the orphan, that is sufficient to show that the configuration is a Gardner fitting configuration, right? So actually, this algorithm finds an orphan, right? Okay, let me continue this part. So only unique nodes of one level are extended to the next one that I have said, and the equal set of nodes not extended, and they are called the frontier nodes. I have said, okay, and in this way I have to proceed. And see, it's important. It's important that the process, the algorithm will eventually terminate. Why? Because your although C is infinite, S set is finite, right? S is finite. So therefore, it's a number of unique nodes. There is number of nodes also finite. Okay. So some possible of subsets of SM, if S is by set of state and M is by neighborhood. So therefore, number of unique nodes, they're finite. Number of nodes, in fact, they're finite. Okay. So therefore, since it is finite, the algorithm will terminate. Hmm. And the uh, uh, to show the characteristic of the algorithm, it is very important to show two things. First thing is it will terminate. Okay, here is important. Although we are dealing with infinite configurations, but it will terminate. Okay, so and when the algorithm will declare it is surjective, if it finds no such terminal node, all the nodes, they are the sometimes you'll be able to get the frontier nodes, but there is no terminal node. Okay, and if there is no terminal node, then it declares. Okay, and all are and you didn't get any node to explore. When you explore, you get a new node. If you get a new node, then you explore. If you don't get a new node, and if you see all the nodes are the frontier nodes, nothing to expand, then you declare is complete. You declare tree is complete, and then you declare CM is surjective. Here, in the example I have given here, the algorithm here the algorithm process terminates by saying the given rule, okay, or given CA is not surjective. And here what I get, the orphan configuration is so 1 0 and then any configuration you consider. So if there is a pattern like this, okay, 1 0 0 etc., you'll get that orphan. So I have taken in the example, I have taken this all 0 1 then 0. So if I append through here, if you append 0 then 1 then all 0, right, uh, you'll get a I mean Gardner Fitting acceleration. Okay, okay. So now let us take another example to show the subjectivity test. This is my next rule. Again, for simplicity, I have taken binary rule, right? Here, this is the rule 30, famous rule, Ultra's rule 30. We have discussed about rule 30 before. Oh, this is rule 30. So now you construct, as I've said before, as I've said, you construct in this way. So you have taken 0 like before. So all the neighborhood configuration for which next value is 0, that constitutes, I mean those constitute the node. So here 0 0 0 0 1 0 0 1 1, sorry, 0 0 0 1 0 1 1 1 0 and 1 1 1, they are all 0, right? So they form the the root. So from this one, see, you using the similar style, you develop the elements of next node, next level nodes. So it was 0 0 0 0 0 0. From that, from 0 0 0 you will get 0 0 0 and 0 0 1. From 0 1 from 1 0 0 you'll get 0 1 0 and 0 1 1. In this way you'll get 8 entries here, and they are distributed in this fashion. So it's 0 0 1 0 1 0 0 1 1 1 0 0, and you'll find, so I'm not I'm not here going into detail. So you'll find that these two nets, these two nodes, interestingly, they are equally distributed. 4 in first node is 4, right? 4 entries, and in second node there are 4 entries, right? So now, and you get a frontier node here, like before you get a frontier node. So you have to expand only one. Okay. So 0 0 0 0 1 0 1 0, etc. You are getting again two nodes, but one is frontier node. Okay. 0 0 1 0 1 0. The first node, the uppermost node, is same of level 2. N1 of level 2 is equal to N1 of level 1, right? So you can get the frontier node. Hmm. And the lower one is again a frontier node, 0 0 0 0 1 0 1 1 1 0 1 1 1. This is also same with the root. Then what to do? So all are explored. You can't expand it further. So tree has become complete. And then you can declare, okay, since it is complete, then you can declare that it is surjective C. So rule 30 is a surjective one. So in this way, so if you find no node to expand further, then you can declare, then the algorithm declares the CA as surjective C of whatever. Okay. So all the nodes, frontier nodes are cost terminals. So there is no terminal node, so it's complete. Now, important part is the proof of correctness. So this given this lemma is like this: for an arbitrary cellular automaton, local map R determines a non-sidereal parallel map if and only the graph constructed above contains the terminal set. So this is the statement of a lemma, which was you can find in the paper, and we also proved. I am, I'm saying that you prove it by yourself. Huh? I mean, the proof is given here, so I shall share this slide with you, but I can't continue more today. So you see the lemma, and it is not very difficult to prove. So you do it by yourself. Okay. So this is the algorithm. So uh, next day we shall cover the injectivity test. Surjectivity is simpler, but injectivity test, it has several issues. Any questions you have?